a shape or figure means to change it. In general, we can change the size, location, or direction that figure is facing. All right, the figure before a transformation is called the pre-image. Very good. Or the original figure. After a transformation, the new figure is called the image, which we did learn that the other day. So image should go there. If the pre-image were labeled A, the image would then be labeled A prime, pronounced A prime. Okay? All right. So now we've got some examples, and they're telling you here's A prime. So what I do is I generally draw myself an arrow from one to the other. Because by me drawing my arrow, it's like, well, what did I just do? What did I just do with my arrow? I slid it, right? It was a slide. Or slid over here, but slid. It was a slide though, right? Okay? And so what kind of transformation is that? Translation. Which is also kind of a funny word because what else does the word translation mean? Where do you normally hear that word? In language. We're translating a language, so we're changing it, right? We're trying not to change its meaning, it's just in a different format. Okay? So the key word here would be slide. All right? Okay, now let's look at this one. It went here, and it went over here, but what do you see there? Yeah, so this is kind of like a what? The word I'm looking for. A mirror. Mirror, that was what I was looking for. That's like a mirror. So what kind of a transformation did you think that one was? Reflection. Okay, and where could we turn that word? With a mirror in your eye. Flip over is another keyword that you might hear. Okay. All right. Now let's look at what happened here. From C to C prime, it went like this. So my arrow, it turned, right? So it turned, and what was that? Rotation. Okay, and then the brain pop didn't talk about this last one, but what did it do? It shrunk, right? So what would that be? A dilation. All right, it's a dilation. Okay, so what I'd like for you to do is take a minute to figure out maybe some real world examples of where you might see some of these things in the real world, okay? Okay, who came up with something for a translation in the real world? Where might you see something? What do you think? Zena? Okay, but we're talking about this mathematical way. Uh-huh. What do you mean? Yeah, but is it sliding it down? Uh-huh. Oh, okay. So like a car driving down the road, because it's still a car here and it's still a car here when it just slid. Okay. So car driving. I'll go with that. What else you got? Oh, that's a good one. Escalator. You know when you're on an escalator. And I think that one you have more experience with than the one that's on my notes. The one on my notes says conveyor belt. Y'all even know what that is? Yeah. It's like in the factory, like with something being made, right? Oh, or like those people movers in the airport, right? If you want to stand there instead of walking through, you can. That's like kind of like a conveyor belt.
How large is it? Like, how large is it? Like the thing that carries the luggage. The airport at Trombone.
So the luggage, luggage cart, sure.
A Trombone because you have to like slide it, kind of, and then a printer you basically starts to do that.
Well, that's what she said too, but I don't think so because you're not the image is not moving. So I'm being careful on that. Okay, what about reflection? Where did you come up with a real life reflection? Anything on a mirror. So think about in real life, where's another place besides a mirror where you might see a reflection? Sarah? Oh, okay. in nature?
Water.
What about the water? On water, right? Like if you're looking out at a pond or something, it's really still water. It's like a really good reflection. Okay. How about a rotation? Somebody knew, right? Oh yeah, like a tilt-a-whirl kind of thing. Those things. Yeah. Okay. What else? How about just a wheel? Right? Something easy. Easton, what did you get?
I was thinking,
But they're going around like this,
I know they're still.
but they're not. Well, it depends. See, the Earth orbits the sun, but we also rotate on an axis, right? And so if you were modeling that, it would actually be like this. So if we're talking about an actual rotation, I would say the Earth's rotation, but not just the orbiting, because I can stay still like this. I'm not actually rotating. Okay? We gotta move on. Dilation. So give me an example of a dilation.
Eraser.
Say it again.
An eraser.
How's an eraser a dilation?
When you use it, it shrinks, you know?
Oh, yeah. It doesn't really keep its shape. That's exactly right. Because if you let's just say I have an eraser that's this big and I use it, it's not this big. It's not the same shape necessarily. What else you got?
Maybe like a model or something?
Yeah. Hello. Scale, models, and drawings. Okay. But there's one John said.
I was going to say a photo, but I can say anything.
Yeah, you can enlarge a photo. That's a scale drawing. What else, Carla?
When they change the volume of it?
How about something on your body? There's something that dilates on your body. Your eyes, the pupils. Right? When someone shines a really bright light into your eyes, your pupils what? Shrink so that it keeps the light out, right? But when you go to the eye doctor, they put drops in your eyes to make your pupils dilate bigger so that they can what? See into your eyes to get a better picture of what's going on, okay? All right, so we did our rainbow. All right, we did that already, right?
Yeah.
Now I see where it is. All right, okay, and we need to pick up our pace. And I'm sorry that I'm feeling weird, okay? Okay, these two words, congruence and orientation. Congruence, we already talked about. What does that mean? Same size, same shape. Congruence refers to whether the pre-image and image have the same size and shape. Okay, but the second word you may not know, orientation of the figure, refers to whether the pre-image and image are facing the same direction on the coordinate plane. Okay, so what I mean is, I am vertical right now, but if I lay on the ground, did my congruence stay the same? Yes, but did my orientation stay the same? No, because I was vertical and then I would be horizontal. You see what I'm saying? So some of them preserve both, some of them preserve none, some of them preserve only one. Okay? All right, so orientation of the vertices refers to the order in which the vertices are labeled clockwise and counterclockwise. We'll get to this one more later when we get to rotations. Okay? So super quick, you can see, look at the picture, label the type of transformation shown, and then state if it appears to be congruent between the pre-image and image, and then if the orientation state. So first, let's look. It went here, now it's here. What is that? That's a reflection. Does it maintain congruence? Yes. And then what about the figure? Did the orientation change? Yes. And then the vertices, did they change? Meaning, let's pretend that this one is labeled at 1, 1. Where would this one be? Negative 1, 1. So did the vertices change? Yes. Oh, we should write this. We should write change. Sorry about that. So, congruence, yes, stayed maybe to make sure that you understand what you're writing there, okay? Okay, so let's look at number 2. It went from here to here. What is it? It's a translation. Did it keep its congruence? Yes. It stayed the same. Okay. Did the orientation change? No. So I would say that this stayed the same. What about the vertices? They did change. Because what made them change? Yeah, they moved, right? So of course they're not going to be the same. Okay? All right, what about number 3? What's happening on number 3? Yeah, because it was here and now it's here, so it got bigger. So it is a dilation. And did it preserve its congruence? No. It got bigger. Okay. What about the orientation? It stayed the same. What about the vertices? Changed. Okay. And then finally, it was here, now it's here. What is it? It's a rotation. Did it maintain congruence? Yes, it is exactly the same thing, it just turned. So the orientation changed and the vertices also changed. Okay, so this is the most basic of all of this stuff. Remember when I talked on Monday when I was looking at the week and I said transformations begin? All of this is this one big unit, okay? And this is just an overview, okay? What we're going to start doing in a minute, we're going to delve into dilations. Tomorrow we're moving on to reflections, and Friday next week we hit translations, and after Thanksgiving, rotations. So it takes us a while to get through all of this. You might be like, why is this taking so long? Well, we haven't really done any math yet, that's why. Okay? All right, see if you can try this on your own, okay? Let's see how you did. It says, 2 people graph the transformation shown below in 5 through 10. Record which graph meets the given criteria, writing live, or Hassan, both, or neither. Okay, so let's look at number 5. Represents a reflection. Well, you know what I think I would do first is I would look at these pictures. I look from here to here. What's that? That's a translation. No, because that's right. In order for it to be a reflection, then this would have to be O. You got to be careful. You can't. Thank you for saying that. You cannot just look at the shape. If you were just looking at the shape, you're exactly right. It could have been a translation or a reflection, but because of the letters, and I'm pretty sure coming soon to a classroom near you, there's a test with something like that on it. Be careful about the letters, okay? All right, and then what's this? That's a reflection. Okay, so now, who represents a reflection? He does. Number 6. The image is in quadrant 1. The image, so what does that mean? The new, the one with the prime, is in quadrant 1. Oh, we better review that. Where are quadrant numbers? Where's 1? Right? Then what? 2, 3, 4. Okay, if you ever forget how to do this, it's positive is like where you learned in elementary school. So that's where you always started. And then make a C. Okay, and it goes around like that. So if you forget the order. Okay, that will be important, especially when we get to rotations. Okay, so which one has the image in quadrant 1? Live. Preserve congruence. Both. Change the orientation of the figure. What do we think? Yeah. The other one didn't stay the same. Change the orientation of the vertices. I would say both. Oh, orientation. Well, I still would say both. What would you say? Oh, they say just as on. I think it's both. Change the size of the figure. Neither, because did you notice what is the only one that changes the size? Dilation. That's exactly right. All the rest will which is why the brain pop, did you ever wonder why the brain pop didn't talk about dilations? Yeah, because translation, rotation, and reflection, all it did was move it, right? But a dilation, you're shrinking and growing, okay? All right, so now we're going to get to the other paper, which is just about dilation. Well, if we, based on our definition, and we said the vertices, like, if this is 2, 1, and this is now negative 2, 1, it changed. This is 2, 2, and this is negative 2, 2, it changed. Basically, any movement is going to make it. Okay, now we're moving on to strictly dilation, okay? All right. A dilation, let's see what you can do here, is a transformation in which a figure is made larger or smaller with respect to a fixed point called the center of dilation, okay? In this grade, so I'm going to put 8th grade, it will always be the origin. What's the origin? The center of the graph. In algebra, you can do a dilation around any point, around the point 2, 4. That's a completely different mathematical skill, which we'll learn next year. I just want everyone to understand, when you keep hearing these phrases, the center of dilation, you're like, let's never put anything else up because next year it's going to change. Okay? The ratio of the side lengths of the image to the corresponding lengths of the pre-image is the scale factor, or K, of the dilation. Well, that makes sense. What it's saying is the side lengths of the image. The image is the new one. The pre-image is the old one. A ratio is written like that. Now, does it look familiar? It was just a big lengthy sentence, okay? For dilations, the pre-image and its image are, what do you think goes here? Similar. Okay, so I've got a little picture. This would be called the center of dilation, which, like I said, for this year, it's going to always be the origin. Okay? If we're going this way, what's happening to the figure? It's growing, so it's dilating bigger. Tell me about K. There you go. It would have to be greater than 1. Remember that from the other day when we talked about scale factor? When we said that scale factor is greater than 1, the image got bigger. Okay? So if I'm going this way, though, this is my original, and now I'm going back to here, it's shrinking. And what would you say? That the scale factor has to be less than 1. Okay? And then remember, in math, the word dilate means to reduce or enlarge. Yeah. Look for some. I was just looking for something. Okay? All right. Now on the bottom, I think you can probably dictate to me. Let's see what you can do. Okay, so now let's actually do the math. We already know what's happening in dilations. Now let's do the math, okay? So, dilate a figure with a scale factor greater than 1. So what type of a dilation is it going to be? Enlargement. Okay? So it says graph the dilation using a scale factor of 2, and 0, 0 is the center of dilation. You see what I mean? Where it says 0, 0 center of dilation, it's always going to be that here. Okay? Here are your steps. 1, identify and record each point in the pre-image. So right here, T, what would T be? 1, 1. 1, 1. And what is D? Negative 1. Negative 1. And what is S? 1, negative 1. Okay, if you're not sure, there's the origin. Might be easy to put that on there. Remember, for T, 1, 1. D, negative 1, negative 1. S, 1, negative 1. Okay, so I remember how to do that. All right, step 2. Identify the scale factor and predict if it will expand or shrink. Well, the scale factor is 2, so that means it's greater than 1. So what's it going to do? Expand. Step 3, multiply the coordinates by the scale factor 2 and record the new coordinates. So guys, look right here. If I have a rule, x, y, what am I going to do with x and y? Yeah, 2x, 2y. I'm just multiplying everything by 2. And now actually do it. So 1, 1 times 2 would be 2, 2. Negative 1 times 2, negative 2, negative 2. And 1, negative 1, 2, negative 2. And then finally it says to plot and connect the new points and label with prime notation. So go ahead and put 2, 2, T prime. Okay? Once you're done, take a look at your image. Is it a similar figure to the original?
Yes.
Yes. If it's not, what happened? You did something wrong. My first thing would be to check these numbers, make sure that you actually labeled them correctly, then check to make sure you multiplied correctly, then check to make sure you plotted correctly, okay? Because if you don't get a similar figure, then something's not right. Okay? All right. Let's try this one. Example 2. Graph the dilation using a scale factor of 0.5. So this is going to be a scale factor less than 1. What is this going to be? A reduction. Perfect. We're going to do the same steps. We're going to identify and record each point in the image. So here's our origin. Where's n? Negative 1, 4. Go ahead and finish them out. Okay. Now, the scale factor was 0.5. We're predicting expand or shrink. Well, they already told us it's going to shrink. But why is it shrinking? That's right, because your scale factor was less than 1. Multiply the coordinates by the scale factor 0.5 or 1/2, whatever is easier for you to think of it, because 0.5 is the same as 1/2. And so for the rule, what would you write here? 0.5 x or 1/2. Those are the same. Okay? For both. And now we're actually going to multiply. Well, half of negative 1 is what? Negative half. Half of 4 is half of 3, half of 1, half of 0, 0, half of negative 3, negative 1.5, half of negative 2, and half of 0, 0. And then finally take those points and plot them on the graph and then label. Okay? And it's not perfect. If you look at mine, mine's a little shaky, but is it a similar figure? Yeah. Okay? And again, the proof is that you can see that the pre-image was bigger than the image. We had a scale factor less than 1, so it all worked out. Okay? Done pretty good so far? Almost. Okay, we got one more that we're going to do together. Okay, on the next page. All right, it says you must identify the points this time on the coordinate plane and then dilate it by the scale factor given. Okay, so what we're saying is they've already been dilated. Okay, that's the difference now. So which one is the original? Small or big? The small one, and so that means the new one is the bigger one. And how did we know that? Because the prime marks. That's exactly right. So go ahead and write your points for the original. Go ahead and label them A, B, C. Okay. Label the points for the new one. Okay. Okay, and now let's fill in this sentence. This is a or an blank because the original figure is getting blank. What would you say? This is an enlargement because the original figure is getting bigger. Good. This time, though, we have to find the scale factor. They gave it to us before, but see, they've given us both shapes this time, so they want us to find it. So how are you going to do that? Well, what I would do is I would pick a point, okay, that's not 0, which in this case, there are no zeros, so don't worry about it. Okay, but just pick any point to deal with. So I would pick this one. All right. The new point was 2, 6. The original point was 1, 3. Well, 2 over 1 is what? 2. 6 over 3 is what? 2. So the scale factor is 2. Notice that it had to work for both of the digits in the point. What I mean is, if I had gotten 2 here, but then maybe I got 3 here, something's not right. That would be like, remember when I'm getting ACCA confused with CAP. And we first did similar figures in ACCA, so I don't think this would have been you because I wasn't here. But I talked about when you grow or shrink a picture, right? A similar figure. You have to grow it or shrink the length and the width at the same rate. Yes? You do that all the time with photos, yes? Because what happens if you don't? It gets distorted, and now you have a similar figure? No. You see what I mean? So that's why both of these points have to move at the same rate. Otherwise, you just don't have a similar figure. Okay? All right. And then finally, the algebraic equation used to dilate the image would be xy is what? 2x, 2y. Because remember, that's what scale factor is. All right? Okay. I really wanted you to do both of these, but let's just pick one. How about just do number 3? Okay? Take a look.